presentation. Two presentation of 30 minutes each, plus 15 minutes questions. First, Robin Varennes, and then Veranda. So please.
Thank you, Yannick. So hello everyone. So first of all, I would like to warmly thank my co-authors and particularly Guillaume for both organizing this event and also give me the opportunity to present today. And also I would like to mention that this is my third year of PhD, but this is actually the first time that I do an actual conference, not online. So I'm really glad for this. So let's jump into the presentation. So I will talk about the interplay between magnetic braking and turbulent stress tensor regarding plasma flow. So this is a talk about fusion. So we'll talk about tokamaks here. And as I know that there is a lot of non-specialists here, I will just take a step back to take a look at the system. So basically here is a sketch of a tokamak where I define the toroidal coordinates. So there is in red here the radial coordinates, and then we have two angles. One is the poloidal angle, so theta, and the toroidal angle phi. And basically, we'll take a look at rotation in this talk. So I will define two useful quantities. The first one is the toroidal velocity here, and the other one is the poloidal velocity, which goes in that direction. And for this last one, in the fusion community, usually we talk, this one goes at the same rate as the quantity that we call a radial electric field. And so this is basically this value that we will take a look into. There is also two other quantities that define toroidal systems. So there is a major radius of the system, which is R0 here, and also the minor radius, which is called A usually. And also in this presentation, I will talk about so-called radial profile. This is some figures that I will show throughout this presentation. So I will just show you what they mean. So basically here is the radial profile of value x. And so on this x-axis from left to right, it means that we go to core plasma to the edge of the plasma. And basically it goes to 0 to 1, where 1 is the last closed magnetic surface. So now that we define all this, we can just, let's say, talk about the meaning of this presentation. So basically the thing is that in tokamak, the magnetic configuration is often considered axisymmetric. And axisymmetric means that you have symmetry in the toroidal direction. But let's say that there is a renewed interest for the impact of 3D magnetic perturbation. So let's say to have a fluctuation in the toroidal direction of the magnetic field. And there is many reasons for this. For one could be that the threshold for the LH transition can change under the impact of those perturbation. It had been shown that it can optimize the plasma stability and confinement. And the one that would be of interest today is its impact on the rotation. So basically, we will mainly talk about the toroidal rotation. And so we can ask the question, why are we interested in the toroidal rotation? So basically, it is because it plays a key role in the confinement. And the confinement is really the key element for fusion. We want to be able to confine heat and particles so we can reach fusion condition. And the point is that, let's say in most tokamaks, we could control this velocity using external momentum, for example, coming from the neutral beam injections. But in reactor-sized tokamaks, for example, ITER, it will be the first one. It will be challenging, if not impossible, to control because the plasma volume is so large. And so the flows will be rather governed by what we call intrinsic rotation, which means that the plasma will rotate in tokamaks even without any external momentum. And so basically, this is the aim of this presentation, is to understand the mechanism behind this intrinsic rotation. And so we will see that it is governed by two mechanisms. The first one is the turbulent momentum drive, and the other one is called the magnetic braking. And this one is coming from the effect of 3D magnetic perturbation. So it can come in tokamak from external perturbation like RMPs. So we mentioned that yesterday. And the one which will be of interest for us today is the magnetic field ripple. So the magnetic field ripple, if you look on the figure on the top right, is the effect of, it's the name given to the modulation of the magnetic field due to the finite number of coils. So if you look here, you have a view from above of the tokamak. Here you have the direction of the total velocity. In black, you have the coils that generate the magnetic field, and you can see that the magnetic field lines are correlated because there is not an infinite number of coils. And so you can attribute some kind of amplitude to this ripple perturbation, which is expressed in a percentage. So it's a percentage of the axisymmetric magnetic field. And just to show you a glimpse of what I mean by the intrinsic rotation, you can look at the figure on the bottom right, which is a radial profile. So if you remember, on the left, this is the core, and on the right, this is the H plasma. And what you can see here is that it is the toroidal velocity. So sorry for it's not the same notation as here, but this is the toroidal velocity in a torsupra discharge. So torsupra is the tokamak here in France. For different ripple amplitudes. And what you can see is that when you have a low amplitude, the plasma will still have a finite velocity. So there is actually a truly an intrinsic rotation. And when you increase the ripple amplitude, this velocity will change and go towards negative values. So from this point, we can see that there is at least two mechanisms involved in the intrinsic rotation. And this is what we will talk about today. So this is the outline of my talk. So first, we will see how we can obtain a reduced model for the intrinsic rotation. Then we will see how we can validate this model with gyrokinetic simulations. And at the end, I will talk about the synergy that exists between these two mechanisms. So first, let's talk about the reduced model. So first, I will introduce more in detail what are the turbulent drive and the magnetic braking that I talked just before. So first, I will talk about the magnetic braking. So the magnetic braking is the force which is due to the 3D component of the magnetic field. And you can see this as a way to constrain particle trajectories. So here I just show you some example, but there is it's just an example. It's just not let's say exhaustive of how particle trajectories can be modified by a ripple. So on the left, you have a poloidal section of the tokamak. So basically, the torus will be inside direction. And you have the so-called banana trap particles. So if you don't know what it is, basically, it's the fact that particle wants to travel along the magnetic surfaces, so which will be a circle here in this projection. But they also undergo, they explore, let's say, a very magnetic field amplitude. So some of those particles will actually go back and forth, and we call them banana trap particles. And so under the effect of ripple, you can see that the banana bounce point here will drift both radially and poloidally. So this is one of the constraints. And one other remarkable feature linked to ripple is actually the fact that if you look on the right here, some particle can become trapped between the magnetic well formed by two consecutive coils. And those particles will undergo the so-called vertical magnetic drift that exists in tokamaks. So those are just examples, but if you want to really see the effect on the overall plasma, you have to account also for collisions. And this is basically a formidable task for a point of view of analytical calculation. So by chance, a lot of people already did this, basically in the 70s or the 80s. And then they show that you can express the magnetic braking force with a really simple expression, which is written here. Basically, this force takes the form of a cohesional friction that will make the toroidal velocity relax toward an equilibrium value. So that's it for the magnetic braking. So now let's take a look at the turbulent drive. So first, I will just redefine what we call turbulence in the fusion community. So this is a name that we gave to the small-scale fluctuation of the electric potential that can lead at the end to microscopic transport. And so basically on the right here, you can see a result of a simulation. And on the color map, you have the fluctuation of the electric potential. So you can see those eddies here caused by the turbulence. And one remarkable feature of turbulence, and one also counterintuitive, is that the turbulence will force a finite rotation through wave particle momentum transfer. So actually, all this mess basically will actually provide a finite momentum to the plasma, and it will start to rotate in the toroidal direction. And so you can also write a force that is exerted by turbulence on the toroidal velocity, which is basically the divergence of the toroidal Varennes stress. And so once again, there is a lot of people who already work on this, some of them in this room actually, who showed that this Varennes stress, which is actually the fluctuation of the radial velocity and the toroidal velocity, it can be expressed as a three term. So there is a viscous contribution, a pinch term, and also a residual stress, which is actually this one that describes this wave particle momentum transfer, and it acts as the source of momentum, and it's this one that will set the equilibrium velocity. So at this point, I think it is kind of hard to follow if we just take this formula. So I did some kind of simplification. So I hope it's not too insulting for the specialists in the room. But what I did is that I took this expression that we saw just before, and I just rewrite the term just by manipulating the equation to write an expression for the turbulent drive, so the divergence of the toroidal Varennes stress. And so what I did is that it can take the form similar to the one we see for the magnetic braking by defining some kind of effective turbulent friction here that take into account the viscosity and the pinch, and some kind of turbulent equilibrium velocity, that take into account the residual stress and the effective turbulent friction. So I will talk about turbulent friction, but keep in mind that the physics is actually viscous, and it's also a pinch that play a role here. It will be easier
to play that game.
Yes.
How do you? I mean, an important property of the stress is, of course, that it integrates to boundary contributions only. And when you do a Crook model with a C instead of a K, as you are doing, you lose that. So how do you take, there are places where that property becomes very important.
So you mean the property of the boundary condition, right?
Excuse me?
You talk about the boundary condition?
Well, the fact that the integral of divergence pi vanishes up to boundary contributions, the fact that you write it as the divergence of something. So you've replaced that as a divergence form with a Crook model, with C, as Harold Grad used to say in good old days. That's a very serious bit of modeling.
Yeah. So what I can say, basically, I know this is kind of real. I don't think you can really see this as a friction, actually. I can call this a coefficient, which is named this way. It's just to have some terms that take into account the damping rates that exist in the system. Actually, the works that I did afterwards, I did it with all the terms, and I really treat the viscous term as a viscous term and the pinch as a pinch. But I think for the non-specialist, for me, it's the better thing to show is actually some kind of damping rates. So this has no, let's say, physical meaning. What I show here is that there is mechanism due to turbulence that will make the toroidal velocity relax toward a finite value. And this is really what I want to show. But you are perfectly right. This is not the right way to do it for sure.
Well, I mean, it always relates to the problem you're actually doing, but there are problems where you really have a disaster if you go down that road.
Okay, but take in mind that I didn't use that for the actual calculation. But let's say that the main idea stays the same if you use a friction. So sorry about this. This is actually really a viscous term and a pinch term, but let's, for the sake of this talk, let's say that this is basically a damping rate, if you allow me so. So at this point, I just talk about, let's say, the state of the art of turbulent drive and magnetic braking. So the novelty of this study is that now we can take them, both of them on the same account. So basically, you can write an equation based on the conservation of the toroidal momentum, which is written here, which take into account the magnetic braking and the turbulent drive. And if you just replace these two quantities, with the one we saw just before, you can write this expression where you have, let's say, a contribution on the two damping rates due to collision and one due to turbulence. And you also have two source terms. And basically, one way to understand this model is to look on the sketch on the right, which show on the x-axis the ripple amplitude, and on the y-axis the equilibrium toroidal velocity. And the idea is pretty simple, actually. So it says that when you don't have any ripple, so when you have an axisymmetric system, the intrinsic rotation is obviously driven by turbulence. So this is the asymptotic regime in orange shape. And when you have a really strong ripple amplitude, and you can consider that the turbulence contribution becomes negligible, you can say that the equilibrium velocity will go towards its let's say collisional prediction. So this is the asymptotic regime in blue. And so the link between these two asymptotic regimes can be really complex. So it's a lot involved here. But there is one interesting feature, which is that you can define a criteria that we will call the critical ripple amplitude, which is a value for which the equilibrium toroidal velocity will be the average between those two asymptotic regimes. And so this quantity is useful because if you know where the ripple is in regard to this threshold, you can know if you are dominated by turbulent, the turbulent drive, or dominated by the magnetic braking. And what is interesting with this value is that it only depends actually on the damping rates associated with the magnetic braking and the turbulent drive. So here you don't have your prediction for the finite velocity due to collision, or the same for turbulence.
Wait. So when you show the first figure,
yes,
about the region from west, but you had the highest variation.
Yes.
When you have the smallest ripple. In this case.
Yes.
But in your figure, so if the delta goes to left side,
yes,
you have the highest effects from collisionality, but
from ripple actually. Basically, you can see the effect of ripple as a collisional let's say physics. I don't know if that's answering your question.
okay. So can you go back to the
Sure.
Okay. So I was wondering, so if delta goes to left side,
yes,
that means the small ripple, right?
Yes.
But then you have to.
And then the equilibrium toroidal velocity will go towards its turbulent prediction, and this is kind of what you can see on the figure as you want to see. So basically, when you go down on the ripple amplitude, so the blue curve, you go up towards the turbulent the turbulent prediction. And when you increase this value, you go down and you go toward, let's say, the collisional prediction.
Okay, thank you. Okay.
So we can define a critical ripple amplitude, and just before going into the, let's say, the simulation stuff to see if this model actually means something, I will just show you a scaling that we can obtain pretty easily for this value. We can basically divide a real sum to obtain the critical ripple amplitude. So it takes this scaling, where you have different values here. So basically, it depends on the coils number, which makes sense because ripple is actually due to the finite number of coils. But you can see that it has a really weak scaling, so this is a square root here, which means actually the number of coils do not impact severely this criteria. But it mainly depends on the ion armor radius and also on the temperature gradient length, which makes sense for this last one because this is the drive of the turbulence. And also there is a strong geometrical impact. And so basically, if you just apply this rule of thumb near the edge of the plasma for a torus supra discharge, you obtain a critical ripple of 0.4%. And at this location in Torsupra, you are way higher, so something like 3 or 4%. And accordingly, when you look at the experiment, you see that the rotation is controlled by the magnetic braking. And so one interesting, I think, exercise that you can do is just to scale this discharge with the ether geometry just to see the impact. And if you do this, you can see that the critical ripple amplitude will go down to something like 0.15%. And so basically it means that maybe we should take a look at this for future reactor. And for ITER, for example, for some discharges, we expect the ripple to go up to more than 1% at the edge. So this was it for the reduced model. So now I'll talk about how we validate it with a gyrokinetic simulation. So for this, we used the code Gisela, which is a kinetic code that solves two equations. The first one is the Fokker-Planck equation, which makes evolve the distribution function in time and which depend on some collision operator. And there is also the Poisson equation, which self-consistently makes the electrostatic field evolve. And here I will show you just a video of a typical Gisela simulation, where you can see that Gisela is able to simulate the whole plasma domain. It has some improved boundary condition, and also it is capable of describing the turbulence properly. And one thing interesting about this movie, which actually is not linked to my work, it's just like, let's say, a publicity for Gisela, but I think it is interesting, which is that you can see that the poloidal rotation, actually, you can see the poloidal rotation that appear, even though there is no external momentum. And so it means also that there is here a mechanism of intrinsic rotation in the poloidal direction. It is also due to a competition between neoclassical effects and collisional effects, and turbulence. And so basically the work that I do here is the same, but looking in the toroidal direction. And so what we want to do is to validate this critical ripple amplitude thing. And so basically I just rewrite the criteria. So regarding the simulation, we have two things to take care about. So the first is to find a way to let's say, quantify this value. So which I won't talk about, but we did this for, let's say, one turbulence. What I mean is that we did that for one set of initial temperature gradient and density gradient. So we will always use the same simulation here, but we will make some variation for the collisional friction. So here it's supposed to be cold, so it's not high, it's cold. And for this, we require some kind of 3D magnetic perturbation to be implemented. So this value is finite. So this is what we did. So we implemented the ripple inside Gisela. And then we made some assumption to be in accordance with the model. So what you can see here on the right is the radial profile of the ripple amplitude that we used, which is drawn in red. So as you can see, we took a radially Gaussian ripple, which is way, let's say, far from the realistic ripple, who would be exponential from core to edge. But we did this because boundary condition, either in a realistic condition or in simulation, acts as a momentum sink. And this one is not included in the model and would make things way more complicated. So we just use this model ripple. And please take care of the fact that we define here delta 0, which is the peak of the amplitude, which we will use to describe the different case for simulations. And so also we did a lot of work to benchmark that the implementation of the ripple was correct. So here I just rewrite the expression of the magnetic braking force. And basically this force appears in the toroidal momentum conservation. So this is the first thing that we checked, and we saw that it was properly conserved in Gisela. And also in this expression, there is two quantities. So the collisional friction and the equilibrium velocity, that are that depend on the collisionality and the ripple amplitude, and these are known with the analytical theory. So we wanted to check if Gisela was able to recover those results. So here I just show you some example on the right, where you can see that we compared the VCall here with the analytical model and also with another code which is called NEO, which is basically a reference to study those collisional processes. And you can see here we did this for one ripple amplitude and for a range of collisionalities. And you can see that we have good agreement. And we did the same exercise basically for the collisional friction. This time we weren't able to use NEO for this, but still we see that there is a good agreement between Gisela and the theory. And so at this point, we were in a good, let's say, shape to test our model by launching self-consistent simulations that take into account both the turbulent drive and also the magnetic braking. So basically what we did to test our criteria was if you look on the bottom on the right here, you can see a radial profile of the, let's say, collisional friction. Let's say it's a damping rate due to turbulence. And we designed, thanks to the theory, some collisional friction in a way that we are way above or way below this criteria. And so if the model is correct, what it means is that for the high ripple case, so the dark blue here, this case should be dominated by magnetic braking, and the one with low ripple should be dominated by turbulence. And this is what you can see on the figure on the bottom right, which shows the time evolution of the toroidal velocity on the top and the radial electric field on the bottom. So if you remember, this quantity is related to the poloidal rotation. And I did this for 3 cases. So one case without ripple, which act as a reference case, so which is axisymmetric. So this is driven by turbulence alone. And the 2 cases that I just discussed before. And what you can see is that the low ripple case show no significant difference with the no ripple case. So this is really driven by turbulence. But the strong ripple case is clearly driven by the magnetic braking, either regarding the toroidal velocity and also the radial electric field. And basically, we see that this behavior, even though this is a fictional ripple, qualitatively, it holds with experiments. So basically, in a Torsupra, Jet, or GT60, we see this kind of behavior with a strong ripple. So basically here I just show you the competition that exists between turbulent momentum drive and the magnetic braking regarding the intrinsic rotation. But we can go a step further and to look about the crosstalk between those 2 mechanisms. So the synergy that can exist between magnetic braking and turbulent drive. So here I will just cut to the chase and show you the results that we have in simulations. So basically what we observed is that the turbulent drive has a negligible impact on the magnetic braking. However, we saw that the magnetic braking can have a significant impact on the turbulent drive. And for this, there is a list of all the mechanisms that can happen. There is the up-down asymmetry of magnetic surfaces, which here does not impact our simulations because we have circular magnetic surfaces. That could also be the impact of stochasticity of the magnetic field lines, but in the simulation we don't have electromagnetic features, so it cannot be this. But there is 2 other candidates that are well described in the code, and the first one is the modification of the turbulent intensity radial shear. And the other one is the modification of the radial electric field radial shear. And so we explored these 2 ways to see if there is an actual synergy. So first we will talk about the turbulent intensity shear. So first let's define what is the turbulent intensity. So there is many definitions among the fusion community, I think, but we will use this one, which basically goes as the perturbation of the electric potential. And here you have the particle charge, and it's divided by the temperature. But basically, the main player here for our simulation is fluctuation of the potential. And let's say the mechanism for which ripple can modify the turbulent intensity is because the ripple acts as a toroidal harmonic with a periodicity equal to the number of coils of the magnetic field. And this perturbation will reflect on the electric potential. And the thing is that when you have turbulence, there is also a lot of other modes that are excited. So it's called the resonant cone. And the idea is that there can be some spectral coupling between the mode destabilized by ripple and the one destabilized by turbulence. And basically what you can see on the figure on the right are some spectra of these modes. So what you have on the x-axis is the toroidal mode number. So this is basically, it describes the fluctuation that goes into this direction, so the toroidal direction. And on the y-axis, you have the toroidal mode number. So this is the same for in the toroidal direction. And what you can see here, so I did this for different ripple amplitudes. And so for the case without any ripple, you can see that there is some sort of cone, which is called the resonant cone or the turbulent cone, if you want, which are all the modes destabilized by turbulence. And when you add ripple to this, you add all of these harmonics. So you can barely see them. So I would just add here the modes that are stabilized by ripple. So this one. And the thing is that the turbulent modes and the ripple modes can couple through mode coupling. And as you can see, we can clearly see this when you increase the ripple amplitude. There is some new modes that will broaden the turbulent spectrum. So this is an effect that we saw in simulation. But you can also notice that here it's in a logarithm scale. So maybe this effect is actually weak. And this is exactly what we saw. So with this, we were able to calculate the turbulent intensity. And so here I can show you the result from simulations. So on the right, you have the radial profile of the turbulent intensity for different ripple amplitudes. So, and you can see that from orange to black, you increase a bit the turbulent intensity, but the effect is really weak. Even though this effect is well described in the code. And so basically, the second effect is the impact on the radial electric field. And so basically, the shear of the radial electric field is expected to impact the turbulent Reynolds stress, the toroidal Reynolds stress. And the ripple is expected to change the radial electric field through collisional processes. So it goes back to the slide where I show you all these trajectories of particles. So at the end, if you do all the calculation, you can see that under the effect of ripple, you can enhance the radial electric field. And basically, this is what happens. So I can show you the figure on the right, which shows both the candidates for the synergy mechanisms. So what you can see is in the top, you have the shear of the turbulent intensity. So basically the shear of the quantity that I showed you just before for the different ripple amplitudes. So from orange to let's say dark blue, you see that there is a weak effect. And here I remember to use the shape of the ripple amplitude. And at the bottom here, you can see the effect on the shear of the radial electric field. So you can see that there is strong effect, especially near the core of the plasma. And this was associated with an increase on the toroidal Reynolds stress. So you can clearly see the correlation here between those cases. So we can see that there is a strong modification of the toroidal Reynolds stress due to the ripple amplitude, and it is strongly correlated with the radial electric field. So I arrive to my conclusion. So what we saw today is that the plasma rotation is driven by a competition between turbulence and magnetic braking. So that the magnetic braking overcomes turbulence above some kind of critical amplitude of the magnetic ripple. Then we saw that there is some synergy mechanisms between ripple and turbulence. So we saw that the toroidal Reynolds stress is strongly impacted by the ripple. And we see that the main player is actually the enhancement of the radial electric field shear due to ripple, which in turn modifies the stress tensor. So that's it for me, and thank you for your attention.
Question, yes.
magnetic braking depends on the geometry of the magnetic perturbation, the 3D.
You mean the ripple basically depends on many things. So if I just go back to the first one of the first slides, basically it depends on the number of coils. It depends on which, let's say, the shape of the coils also. So basically,
You have a simple expression of magnetic braking
Yes.
Due to ripple. Is there also expression of magnetic braking due to, for example, external application of 3D magnetic?
Yes, actually, it's pretty similar. So here I use ripple because it's most simple for many cases, but you can basically have any kind of perturbation.
Okay, so then my question is, so we can think about the mean of control or by a 3D perturbation on the momentum drive, and then the ripple, does this provide a way to enhance this control or the other direction?
Ripple won't be a candidate, I think, because it is static, so you cannot like change the coils between a discharge or another. But there was some studies to use, for example, RMPs, or so resonant magnetic perturbation, or NRMPs, so non-resonant perturbation, to actually act on this magnetic braking and to change the rotation.
Yes, so what I mean is the ripple, does it act as a catalysis or as a
Oh, do you mean it is detrimental or favorable for?
Yeah,
so I actually I don't have the answer, unfortunately. And if I was to guess, I would say that it really depends on the discharge. If you have a really turbulent discharge, it will be different. If you have a, let's say, a low turbulence or low turbulent drive, and also I think it will be really different either if you are in H mode or L mode, because you don't have any turbulence near the edge for the H mode. So this I cannot answer to you at this point.
So, I mean, I'm a little surprised you didn't pin down the scaling of the residual stress with the ripple parameter. Because, I mean, and the critical thing, there are several components in the residual stress, and one of them is the symmetry braking mechanism. If the symmetry braking is electric field and the electric field is produced by the ripple, that must induce a scaling of the residual stress with the ripple parameter, which becomes then kind of central to the story, right?
So I see what you mean. Maybe I can just help myself with some kind of, so I had some kind of backup slide with, here I just show you some model expression for, here is the residual stress, but this is basically the main player for the rotation, where you have, let's say, all the mechanisms that are, let's say, hidden in there. So basically you have the turbulent intensity, which is hidden in here, and in the K parallel, you have the radial electric field, which is hidden. And I think what you mean is that maybe you can express, for example, the radial electric field depending on the ripple amplitude and inject this in the residual stress.
I mean, the electric field enters through, the electric field shear enters, and how you handle the K parallel. You actually do the sum over modes there. And then, of course, if that is affected by the ripple, that puts a footprint of the ripple strength in the residual stress. So then you have the ripple appearing directly in both terms.
So this is a good idea. So we didn't do this because actually, for example, if we were to express, let's say, K parallel as a function of the ripple, the thing is that all of this is connected to the collisional regimes. And if you want to have a true expression of this, it would be like an enormous, for me, I think, formula. So you will have some non-linearity with the ripple. What I mean is that depending on the collisionarity regime, you will have some regime that will depend at the ripple amplitude at the power 2, one other at the power, let's say 1.5, etc. And so at the end, I don't really know if we can have, let's say, a compact expression of the toroidal Reynolds stress, which is, let's say, tractable with the ripple.
If you show the data, if you show the P residual versus delta,
yes.
Fitting.
Yes, but yeah, I understand. But yes.
obviously you have the data of pi, that's the data.
Yeah, but it wouldn't be true for any charges, right? Because here, for example, we are maybe in the so-called ripple plateau regime, but for another discharge where the collisionality is higher, we will be, for example, I don't know, the how we call it, banana drift.
Then you inform that Steve was talking about this morning.
Yeah, sure. Yeah, I mean, we could do this for sure, but okay.
The other thought that comes to mind is, I mean, why not introduce a third player in the game, namely a toroidal torque? And then you have a competition of the torque, the intrinsic torque, and the ripple. And I mean, you should be able to path smoothly from regimes where the ripple matters and where it absolutely doesn't, because of course, the toroidal torque will directly influence the electric field by radial force balance.
So this is a good idea. The main problem, and this is the same problem that we had with boundary condition, is that when you have 3 players into the problem, it becomes a mess to treat with post-process of simulation results. Because I didn't show you, but there is really a lot of work done just to obtain this coarse grain profiles. And it's really hard to, let's say, deconvolve the effect of each mechanism. At the end, for example, you have a radial electric field that has a shape, but you have no idea if it's dominated by ripple, by turbulence, by other things.
Forgive me, I mean, bugger the code, propose an experiment for West.
Oh,
right, with beams, right? I mean, in other words, one of the classic experiments in the intrinsic rotation was this thing by Wayne Solomon, where he fire a beam, basically a counter beam and gets a stationary plasma, right? So then, I mean, that would be an interesting point to start from, and then see how the ripple alters that.
Yeah, definitely. Yeah.
The idea that's not west. We don't have.
We don't have.
You don't have beams?
We have ripple, but no.
Yeah.
What?
Historically, that was because of ripple, losing all the fast.
Well, I mean, you can, I don't know if P3D has enough ripple. I mean, but I think they welcome proposals from around the world, and you can just tell them you're handicapped, that you'll be welcome.
Jet can do it, because jets can produce artificially some ripple by switching off one code.
I mean, I think that you don't have to cut. I think the impact of this would be much higher.
Yeah, definitely. You can also do this with RMPs actually, or non-RMPs. It's the same model. It will apply the same way.
Can you also get an estimate, let's say, of the absolute value of the
So with the model, yeah, but there is a lot of unknown, let's say, in the system. So basically, if you go back to this, you can have, let's say, some scaling for some value. So let's say the damping weights, you can obtain some scalings. So this would be feasible. Same for the vehicle. But I think the main challenge would be to have a prediction for the turbulent velocity, because it depends, for example, on the pinch, the residual, and the residual stress, the viscosity, and those are not really well known analytically.
changing the flux surface shape would be any impact on
So probably yeah, because so let's say that in the code, etc., we just change the amplitude of the magnetic field, but in reality, if you have ripple, for example, it also changes the shape of the magnetic surface, and at the end, probably it would reflect one way or on the other on this. But to have, let's say, a definitive answer like this, I actually don't know. Sorry.
Other question? Then let's thank our speaker again.